In this video, I'll be introducing piezoelectric actuators and showing how I characterize the behavior of one I purchased from Thorlabs. I plan to use these actuators in a very exciting future project. Now, I know what some of you are thinking. Oh no, not another teledildonics application. But I can put your minds at ease that while exciting, it won't be that kind of exciting. Anyway, stick around for a few videos and I think you'll be pleasantly surprised where this is all going. More to come. There are many types of piezoelectric actuator, but this particular type is built from a stack of individual piezoelectric ceramic elements wired in a series, as can be seen in the zigzag solder connections on the side of the device. The ceramic used is likely lead zirconate titanate, but the datasheet doesn't directly state this, although it does imply they contain lead by warning that they shouldn't be disposed of in a landfill. When a positive voltage is applied to the terminals, the length of the device increases by a small amount. For this device, the behavior is roughly linear, and a maximum displacement of 25 micrometers can be expected at 75 volts. The spec sheet provides a tolerance of plus or minus 15% on the displacement per volt, so my goal is to measure this and ensure it is within spec. For my application, the force generated by the transducer is somewhat more important than the displacement achieved. This actuator can generate up to 1,000 newtons of force, which is about 220 pounds, when it's blocked, which means prevented from moving. Its stiffness is such that at half its maximum displacement, it can generate roughly half of this force. In the future, I also intend to test the force generation capability, as well as its frequency response, but for this test I will only be measuring displacement versus voltage. Here you can see my experimental setup consisting of a digital plunger type indicator with a resolution of 1 micrometer, a multimeter, a 123 block to act as a convenient holder for the device under test, and a granite surface plate to provide a stable platform. Powering the actuator is a linear DC power supply capable of outputting up to 120 volts and 1 amp. Although for this setup there will be negligible current and the voltage only needs to go up to about 80 volts. Here's a plot provided by the datasheet showing the expected behavior of the device versus voltage. Two curves are shown, one for increasing voltage and one for decreasing voltage. When there is a difference in behavior between the forward and backward direction, this is known as hysteresis, and the area between the two curves represents the energy that's lost to hysteresis. Fortunately for this device, the hysteresis is rather small and easily characterized. I will not be measuring the hysteresis today, but it's a good thing to know about when I eventually put the device into a working system so that I can compensate for it. To assemble the test setup, I first put the Gazinta into the Gazouta receptacle. That is, I insert the actuator into one of the holes of the 123 block. I'd previously planned on fashioning something out of Legos, and I totally won't rule that out for future videos, but this block was a lucky find in my garage. It has just the right dimensions to hold the actuator and allow the probe tip to fit inside. It ensures that the actuator stays perfectly perpendicular to the granite surface, and it makes it easy to slide the actuator around until the probe is perfectly centered such that its force is directed down through the piezo stack without imparting any off-axis loads. Stacked piezoelectric actuators are very strong under compression in their long axis, but they are very fragile to other forces or torques, so one must take great care to ensure that they only ever experience compressive forces and never any tension, torque, shearing, or emotional loads. After situating it in the 123 block, I then connect the power supply and finally the multimeter clips. Before beginning the test, I want to know what to expect, so I need to calculate the displacement per volt. I divide 25 micrometers by 75 joules per coulomb, also known as volts, giving a displacement slope of 0.333 micrometers per volt. I intend to gather 8 data points from 10 volts to 80 volts, so the expected displacements are about 3.33, 6.66, 9.99 micrometers, and so on, as you can see on the calculator display. I could have chosen to gather 10 data points, but 8 is a power of 2, and as an enthusiastic dabbler in the computational arts, I just can't help myself. Now let's begin the test. I'm going to gradually sweep the power supply from 0 volts up to about 80 volts, pausing briefly at each intended collection point to let the nerve settle. The displacement shown on the indicator will then be recorded in a spreadsheet alongside the measured voltage. I'll cease narration until I'm done with the measurements because while a picture is worth 1,000 words, a video is worth 1,000 times the number of frames, which is going to be approximately 75,000 in this case. Now that the test is complete, you can see the data values I recorded, carried to a ridiculous 4 significant digits. Yeah, precision police, I've heard it all before. Take your pedantry elsewhere. The rightmost column shows the results of fitting a line through the data. You can see that, as expected, a line fits through the data very nicely. The scatter plot of the data shows how closely the line fits the data. The slope of the line appears to be quite close to the predicted slope of 1/3 of a micrometer. In fact, plus or minus 15% of the spec value would be a range of 0.28 to 0.38 micrometers per volt, while the line fit's slope is 0.30 micrometers per volt. This is a little towards the low end of the range, but still well within the spec plus or minus 15% tolerance. Now I'd like to talk a little bit about how I fit a line to the data. Here you can see the definition of a line, which for many of you is probably triggering traumatic junior high school flashbacks. Y is the dependent variable, which is the function that depends on all of the other variables. Displacement for this data. M is the slope of the line. B is where the line crosses the y-axis at x equals 0, otherwise known as the y-intercept. And x is the independent variable, which is voltage in our case. We need to somehow figure out from our data what good values for M and B should be, so we can plot a line and see how close it is to our measured results. I like to do that using a tiny bit of linear algebra using GNU Octave, which is a free implementation of MATLAB. This linear algebra-based approach ensures that the fitted line is unique and is the only solution which minimizes the error between the fitted line and the data in a least sum of the squared errors sense. The linear algebra definition of a line is A times x equals y. In linear algebra, you work with matrices, which are tables of data, to come up with a best fit between a bunch of data and a mathematical model of the system which produced the data. Here, the matrix A will hold our voltage values, the vector y will hold our measured displacements, and the vector z well, there is no vector z. I just wanted to see if you were paying attention. The vector x is the thing we were trying to find, a vector of parameters. We can solve for x by dividing by, y by a. The values held in x will equal the slope and y-intercept, m and b respectively, discussed previously. Here's a screenshot of me using Octave to solve for x. Doing so resulted in a slope of 0.304 micrometers per volt and a y-intercept of minus 0.45 micrometers. Note that I had already hand-entered the data for a and y beforehand, but those steps have run off the top of the screenshot. With these values of m and b in hand, I was then able to enter the formula for the line in the spreadsheet. You can see that here in the screenshot. It was then just a simple matter of plotting the two columns of measured and fit data as a scatter plot versus the column of voltage data. So overall, I'm happy with the displacement slope that I measured. It was within the bounds stated in the spec sheet, but the limited resolution and accuracy of my measurement device is probably what caused the ripple on the blue line in the plot. However, I think I took enough data that the line fit successfully averaged out the measurement error. So I still got a good estimate of the actual slope. I can now confidently move ahead with other tests, which will hopefully also show that the device is performing to spec in those other areas, such as the force that it produces. And all this is ultimately leading up to building a contraption that employs this actuator as a central component of its inner workings. If you'd like to follow along with this project, don't forget to click subscribe. And until next time, happy basement engineering.